All right, let's now proceed to the question posted or sent by Jeremy. Okay, so this question actually involves eigenvector, eigenvalue, and the general equation. The general equation is actually something you can see from the um, how do you call this one? The formula booklet. So, which I will show you later on as well for you to be able to refer to it. Okay, so let's start. So we have here we have two differential equations here: the derivative of x in terms of t, and the derivative of y in terms of t. So we are asked to find the eigenvalues and eigenvectors of the matrix. So this particular matrix is just actually taken from this. All right. So here the y is 0, so that's why it's negative 4, 0. And then here it's 3, and then it's negative 2. Okay. So if you try to recall on how we do the eigenvectors or eigenvalues, we can write this as negative 4 minus lambda, and we have here 3, and we have 0, negative 2 minus lambda. This is equal to 0. Okay. So for us to solve for the eigenvalues, we have to cross multiply this one. Negative 4 minus lambda, negative 2 minus lambda. Then we have minus, and the cross product of this, which is just 0, equal to 0. So this now becomes, if we try to solve this, 8 plus 2 lambda plus 4 lambda plus lambda squared equal to 0. So simplifying it, we now have lambda squared plus 6 times lambda plus 8 equal to 0. Okay, applying factorization, this is now equal to lambda plus 2, lambda plus 4 equal to 0. So solving this one, we have lambda plus 2 equal to 0. Therefore, our first eigenvalue is equal to negative 2. And the other one, lambda plus 4 equal to 0. So lambda is equal to negative 4. Sorry, this is our second eigenvalue. Now, let's try to have the eigenvectors. So to solve for the eigenvectors, so we need to substitute now the eigenvalues. All right, so let's start with the second eigenvalue rather. So a sub 2 is equal to negative 4. All right, so we can now write this as, we have to be very, very careful with this so that we won't be confused with the signs. Negative 4, then we have minus, I will use red so you won't be confused. The value is actually negative 4. That's the value of our second eigenvalue. Below it is 3. Then we have here 0, negative 2. Then we have minus. Then we have negative 4. All right. So simplifying this, we will get 0, 3, 0, and this becomes 2 actually. All right. Now, when we continue this one, uh, since the upper portion is both 0, all right, so maybe we can use the lower portion. So the lower portion here, since this is the x and the y, x comes first, so that means this must be the x and this must be the y, the coefficients. So we can now continue writing this as 3x plus 2y, of course, equal to 0. Okay, so from here, we have to solve for the eigenvectors. So we have to solve for, or we have to assume a certain x value and solve for the y. Remember that our x is the independent variable. So we can further write this as, let me write it here so we can use the bottom portion for the first eigenvalue. So I can write this as 2y equal to negative 3x. Remember that I could also write this as negative 3x. Let me put another version on top. Sorry, another version. This is another version because sometimes my negative could be on the y, it could be on the x. So you might be wondering, you might be confused. In my case, why am I having the negative on the x and then the marking scheme, the negative is on the y? Those are the same things. We call them as multiples. So for you to see that, I could also write this, another version of it. Let me just write it here. Another version, which is just the same, is, I can write this as negative 2y equal to 3x. They're just the same. It's just a matter of the negative sign. So if I will use the first version which I have written, 2y is equal to negative 3x, let's assume any x value. If I assume x to be 1, solving for the y, this becomes 2y equal to negative 3. So y is equal to negative 3 halves. But we don't want to have a fraction. So for this to be a whole number, the negative 3 halves, we have to multiply. So let me write negative 3 halves here. Negative 3 halves. Okay, this one. So for this to be a whole number, we have to multiply both sides. By the way, for the fraction to be a whole number, we have to multiply this by 2 so that I can eliminate the denominator. Thus, we have to multiply 2 to both x and to the y. 2 times 1 and then 2 times negative 3 halves. That is why, let me erase this part here. That is why we can actually write this as 2 and then the other one is negative 3. So this is now our second eigenvector. All right. Now, if I'll use the other version, it would still be the same thing. If I will assume x to be 1, so solving for the y, this becomes negative 2y equal to 3, y is equal to wait for a while. It would still be negative 3 over 2. It's the same thing. Okay. Now I get it. What if I assume x to be negative 1 instead? Okay. Let me erase this one. What if I assume x to be negative 1? So if I assume x to be negative 1, this now becomes negative 2y equal to negative 3. So solving for the y, this becomes y equal to 3 halves. All right. So it will be the same thing. It's still 3 halves. To make this one a whole number, we multiply 2 to both x and the y. Therefore, we would still get the same eigenvector, but the negative is now on the x and not on the y. Negative 2, and then you have here 3. So basically, you don't have to worry if the negative is on the x and not on the y. All right? They mean the same thing. They're not actually different. So if I will use this one and then the marking scheme shows this answer, don't worry, they are the same. All right. This time we now go to the second eigenvector. So we now have the eigenvalue. Let me just encircle the eigenvalue. This eigenvalue gives you this eigenvector, either of the two. They're just the same thing. You don't have to write them twice. You don't have to show both. They're just the same thing. This time, let's now have the first eigenvalue, lambda equal to negative 2. Let me just encircle this blue. And then we do the same process. So we now have negative 4 minus negative 2. Then you have here 3. Then we have here 0, negative 2, minus negative 2 here, xy. Okay. So if we are going to simplify this, all right, this now becomes negative 2, 3, 0, and then 0. All right, equal to 0. Oh, wait for a while, sorry. Let me just modify this, write this properly. Xy equal to 0, 0. All right. So in this case, for both, the y is 0. And we have the x. Yeah. So we can just choose, I can just choose either to use the top one, where the x is negative 2. The x here is negative 2, or use the bottom one, which the x is 3. So either of the two, it will give us the same value for the x. All right. So let me use the one on below because it's positive, so it's easier for me to analyze. So this now becomes 3x plus 0y is equal to 0. All right. Or I can write this as 3x equal to 0. Therefore, x here is 0. Okay. So even if I use the one on top, negative 2x plus 0y is equal to 0, still I'll get an x equal to 0. Now, automatically, if your x is 0, it means that your y is 1. So this is first eigenvalue. So the first eigenvector will now be equal to a 0x leading to a 1y. This will always be automatic, right? So that is how we solve the eigenvector and we solved the eigenvalue first, then we were able to find out the eigenvector. Okay, next. So this time, we are now ready to write the general solution of the system. Let's just write first the eigenvector and the eigenvalue. So we have an eigenvalue of 1. The first eigenvalue, which is equal to negative 2, gives us an eigenvector, which is 0, 1. And then the other one, the second eigenvalue, which is negative 4, gives us an eigenvector equal to we can choose either of these. So I'll just choose the positive x to negative 3. All right. To find the general solution, we actually go back to the formula booklet. So it's actually found in the formula booklet. Okay. It's actually here. I've shown this in class before. So it's actually found in AHL 5.17. This is exact. Exact if we find the value of A and B. But if we retain it as A and B, that is general. Okay? So from there, so let me just copy it before I go to Jamboard. So the general equation would be x equals A times E. You have first eigenvalue t, and then the eigenvector, plus the E second eigenvalue t plus the eigenvector. Okay, let me go back to Jamboard. Okay, so here we just have to substitute the values. So you have x equal to A, we have E, our first eigenvalue is -2, then we have T, and then the eigenvector for this is 0, 1, plus B, E. The second eigenvalue is -4, T, and then the particular eigenvector for that is 2, -3. And this is now the general solution. Okay, by the way, we need this general solution in order to do the sketch. I think that's letter C. Let me just take a screenshot of this. All right, let's now go to the next question here. So the next question here, justify. The next question here is for us to justify whether the equilibrium point 0, 0 is stable or unstable. All right. So for us to be able to understand this, remember that this one is pertaining to your x. This one is erase. This one is pertaining to your x, and this one is pertaining to your y. Okay. If we do particular solutions, and if you try to solve this, we can actually think of this A as this one, the first one, and we can think of this B as the second one as well. Okay, I repeat, let me just erase this one here. When we solve for the particular solution, this A pertains to the first 0, which is the x, and this B pertains to this one, which is the y. Alright, so if you recall our lesson on particular solutions to coupled differential equation, so we actually encountered linear equations, systems of linear equations into variables A and B. So we can think of A as this and B as this one also. Okay, so if we focus on A, okay, let's try to see whether the equilibrium point is stable or unstable. So if we try to focus with A, so let's just focus with A first. So this is now A times e to the power of -2t. All right? So since the exponent is negative, I can rewrite this as A over e to the power of 2t. Okay? Now, let's analyze. As t approaches infinity, what happens to your e? As t approaches infinity, if you try to look at it, your e, or sorry, not e, as t approaches infinity, what happens to the value of e to the power of 2t? So as t approaches infinity, the value of e to the power of 2t also somehow approaches infinity. That means it becomes bigger and bigger. Hence, as this becomes bigger and bigger, what happens to the value of your a over e to the 2t? What happens to the value of this? I repeat, let's go from the top. As t approaches infinity, as we go to the right, further to the right, so the value of your denominator e to the power of 2t also approaches positive infinity. It also becomes bigger, in other words. As the denominator becomes bigger, what happens to the entire expression? A over e to the 2t. As you increase the denominator, as you increase the number you divide to the numerator, the entire expression actually approaches 0. It goes closer and closer to becoming 0. Similarly, if we try to analyze the other one, so we have b e to the power of -4t. All right? We could also rewrite it as b over e to the 4t. And using the same reasoning, no? As t approaches positive infinity, let's shortcut this one. b over e to the power of 4t approaches or goes closer and closer to becoming 0. Therefore, since both of them goes closer and closer to becoming 0, which is actually the equilibrium point, this one, the one that's being stated on top. Therefore, we can assume, therefore, we say the equilibrium point, equilibrium, it's the state of being balanced at 0, 0 is, because it approaches, you have seen it, stable. So this is how we show that it really is stable at that particular. Okay? So that's how we justify. Next. This time, let's try to find the value of dy over dx at 4, 0 and negative 4, 0. Okay. So for us to be able to do that, we need to go back to this. We need to have this one again. Copy this one. All right. And paste it here. Okay. Take note that what we are given is dx over dt and dy over dt. However, we wanted dy over dx. So we need to modify this so that we can get dy over dx. Okay? So dy over dx will just be equal to dy over dt multiplied with, let's use this one, but we wanted to get dy over dx at the end. Therefore, we have to cancel out the dt. And the dx should be in the denominator. Dx should be in the denominator, right? And we don't have a dt. So the dt should be cancelled, and we should get an expression where dx is in the denominator. Therefore, we multiply this with a dx in the denominator and with a dt in the numerator. So that later on, we can cancel this. And we can cancel this also. So we have dy over dx remaining. All right? Therefore, we say the expression for dy over dx will just be equal to dy over dt, which is 3x minus 2y, multiplied with dt over dx. In other words, it will just be the reciprocal of this, 1 over negative 4x. Therefore, dy over dx will just be 3x minus 2y over negative 4x. So this is now the expression that we are going to use. All right. So let's start with the first one. So for the first one, we have at 4, 0. So dy over dx at 4, 0 will just be equal to 3. Our x is 4, right? It's given, 4, 0. X is 4, y is 0. So 3 times 4. Then you have minus 2 times 0 all over negative 4, times 4. So if we solve this, this is now 12 minus 0 over negative 16. It gives us negative 3/4 if we simplify that. All right, negative 3/4. So divide by 4, yeah, 3 and 4. So for the next one, so dy over dx at negative 4, 0. So I'll use yellow. So this is now my x, this is now my y. This is now equal to 3 times negative 4 minus 2 times 0 all over, you have negative 4 times negative 4. Okay? So solving it, we now have negative 12 over 16, which still gives us negative 3/4. And that's how we are going to solve the second one. All right. We are now heading to the last sub-question. So we now have here the last sub-question, which is to sketch the phase portrait for the general equation to the systems of coupled differential equation. So we have here from x greater or equal to negative 6, lesser or equal to 6. And that's the same for the y. So first, let's try to prepare this. We can actually draw here a Cartesian plane. Pardon me with my Cartesian plane. So we have here a Cartesian plane here. All right. So we can assume, actually this will just be a rough sketch. Okay. We can assume this to be negative 6 here. Sorry, positive 6 rather. Positive 6 here, this is negative 6 here. Positive 6, negative 6. All right, so take note, this is just a very rough sketch. Okay, so remember, we need to have our eigenvalues, no? Let's start with the first eigenvalue. So for this one, if ever you are asked of the phase portrait, you are going to go back to your eigenvalues and eigenvectors. So our eigenvalues are A1 is actually, if you remember, that was negative 2, right? And the eigenvector for this was 0, 1. Okay, and then the other one is the second eigenvalue was negative 4, and the eigenvector for this was, it's actually, what was that again? 2, negative 3. Okay. So first and foremost, we have to draw the vectors. Okay? So let's draw the first vector, 0, 1. So if you try to get 0, 1, that means we don't have a movement along the x, and then the y is 1. Okay? So the vector will just be, if we try to draw it, the vector will just be this. It passes. Let me erase this one. Okay. So this is actually, let me label it. This is actually for the first eigenvalue. And then the other one, you have 2, negative 3. So 2, negative 3, that means 2 for the x. So 1, 2, estimate. And then for the y, it's negative 3. 1, 2, 3. Again, estimate this one. So if we try to look at it more or less, so I'm sorry if this is not exact. So it's this one. So we can extend this here also. Okay. This is now your second eigenvalue. Okay. Oh, I'm sorry.